Hi everyone, welcome to Math Spellbook. I'm your host Peter, and basically we're going to get into back to where we were yesterday. Basically just doing a little bit of linear algebra and probably learn some more stuff around the way. So I actually re-looked at the problems that I was doing, well actually the problem I was doing yesterday, because it's just a problem with 5 parts. So I did manage to figure out what I did wrong for, I think it was letter D, so I think I'm just gonna basically redo stuff. Hey Tyrion, how's it going? Yeah, with my Twitch titles, I don't really go into specifics because I just love bouncing around with different topics, so that's the reason why the title is a bit broad. So, if you're here for a specific topic, maybe we can cover it, during the stream. The reason why my avatar keeps changing, sizes is because, whenever I look down at my tablet, my camera basically reads that as, oh, I'm going far away from the camera. So that's the reason why my avatar keeps changing sizes. So I am going to put the study clock, and I think we're going to, I'll just disengage my model, and then we're just gonna go forth. I basically Googled distance formulas, and I was oh, that's what I needed to do for this specific question. But I haven't figured out, I think, how to do E and F yet. Distance formula for a point to the origin. Just put a little O there to represent a point, not a plane, which is obviously C squared, giving us 9 equaling 10 square root of 10. Then we have distance I thought you were performing magic. Basically the question is to find the distances that are displayed. So basically A is basically find the distance between a point and the origin. B is find the distance between a line and an origin. C is the distance between a plane and the origin. And D, E, and F are basically distances from either the point, distance from the point to the line, as well as point to the plane, and then line to the point. So I'll just zoom in a little bit so you can see a little bit more. Yeah, and also apologies that I ran a little bit late today, but I managed to get in on a little bit close on time. Probably a minute or two behind, but hopefully you guys can forgive me for that. Anyway, so the line is T being an element of the real numbers. And I think I remember this formula, so it's the origin minus a product of the squared. But what's the best part of your day so far, Tyrion? Yeah, something like that, yes. Actually, this was the part where I kind of stopped doing multivariable calculus because I didn't fully figure this out. distance from the plane to the origin. So I remember that I learned from you guys yesterday that I basically have to find the point that gives us this result. So we'll just pick x is equal to 1 and d is equal to 0. So we'll just pick those results. And then square root of 3 here. Then we're just left with 3. Okay. There are no best parts, only least worst. That's an interesting perspective. Okay. Oh, whoops, no, not the plane. A line. Now this one I had to look up on Google to actually like so this, instead of the dot product, it's going to be the cross product. Should make that a little bit bigger. Drag this over here. Put it over here. Make it easier to see. Then the vector within the line. Oh, hey, Mavoort, how's it going? V is the distance from the line to the origin. Next up, to the point. So R is right. Okay. The plane is x point equals 1. Okay. Distance between a plane and to the normal vector is, for this one, although there's a different way to write this too. probably have to like subtract the difference here. Yeah, like I was actually working through these problems this morning. I managed to figure, like because of the formula, I managed to see why they did what they did for letter D. Now letter E, I have to figure out exactly, because the first one was a distance between a point and a line, which like if you do the cross product of like the difference between with the actual original normal, not normal, but the vector that's in the line, then basically you just are creating like a vector that's sort of like its own little normal vector above where the point is, where the line is pointing towards the line. I mean towards the point, actually. I mean that's how I visualize it actually. Now this one has a normal vector, and the way I'm imagining it is sort of like we know the point is somewhere, like in space somewhere, and we know the plane is here, and I know the normal vector can basically allow us to point towards the point, but we just don't know the... But then again, it could also be a triangle too. I didn't even think about that part. Or like some weird angle. So we have to take into account the normal vector and the distance. So the normal vector will probably doesn't really help much. Because I know from the origin, like if you do the distance formula from the origin, it would be the normal vector times original point times that. But now we actually have to do it from a point. I mean, before when we did, I think this was C, and C turned out to be, let me just double check, yeah, it's that, I was thinking about just multiplying like basically the distance like from the origin from there, but no, that's not how it works. Like, I remember the answer, it's just that like I'm trying to figure out on my own how to actually get there. Because I remembered. Let me see here. Go into my math file for a second. I forget I like put it in my file, so I guess I'm gonna have to Google it. Try and find that sheet that I found. Here we go. This is what I was looking for. Let's see if P is a point in space and sigma is the normal vector is the normal vector of the dot product x equals d is a plane containing a point Q. Then the distance between the plane, or the distance between the point and, okay, so the normal vector is the distance between P and the plane. Use the angle formula in the denominator. So what would be P and Q in this case? I guess we're gonna have to change the plane to a different form of itself. Hey Big Pop, how's it going? Have you ever thought of doing the third body problem? Of course I know it is only situational and depends on which celestial body you're going. I don't think like I know enough math to do the three body problem. Did you guys type anything else in chat? Let's see. It's going to look it up to see derivations. There are two derivations, a geometric one and using differentiation. I can show it if you want. Did you read how to derive the formulas you're using? I mean, do you understand where they come from? Basically, like when I actually applied the formula for D, the distance between a point and a line, I began to understand it when I basically looked at it, because I was like, oh wait, they're actually trying to give you, because like when I saw the cross product, I was like, okay, what is the cross product for? It's basically to find the normal vector of the plane. But of course, like, you know, like how can there be a normal vector with a line? But then again, like when I actually did the cross product of that, it basically tells you a vector that's pointing like perpendicular to that line. So I then, like, geometrically I was able to see that, oh, that's the distance between a point and a line. It's like basically kind of like its own little hidden normal vector that's like pointing towards it. So that formula I managed to figure, like I managed to like kind of see geometrically, which made it much clearer. But this one, I know I'm gonna have to do some mathematical gymnastics with this one. And actually, Big Pup, how's it going? Welcome to the Math Notebook channel, my friend. What's the best part of your day so far? Sorry guys, I'm just like drinking a little tea. Hey Jeff Gross. So far we're doing a little linear algebra. And I guess you could consider it a little bit of multivariable calculus because we're calculating the distance between like planes and lines and point to points, and so far we're trying to calculate the distance between a point, which is r, and a plane, which is p. So I know that the formula for like calculating the distance between a plane to the origin. Plane to the origin, which is the normal vector of the plane, the dot product of its original point, and the magnitude. And what's the best part of your day so far, Jeff Gross? Jeff C. Gross. But now, because basically it says we have to have a distance, we have to have an original point P and Q, and that should be the thing that we multiply, well, do the dot product with n. So now I gotta figure out where I can find P and where I can find Q. So if the so do we use the original point that we used for our original plane equation? Let's see if that works. So maybe that might work. So that would be 0. That would be 3. That would be 0. Let's give this a try. And the distance, then we're left with 3 on top. Oh, okay. Okay. Yeah, I think that is the right answer. Because I remember the answer was like the square root of 3. That's what I had to do. Okay. So we would pick like this is our Q and this would be our P from the plane. Okay. Okay. Now I get it. Interesting. At least I solved that on stream for you guys. You guys are probably like, it's right there. The solution is right there. Okay, what is the last one? What is the last one? Oh. Don't want to be fooling around. Oh, come on. Distance between the line and the plane. So we have the line and the plane. So the line, geez, that is so messy. Oh, hello, Surino. What's the best part of your day so far, Surino? Dang, I can't even make curly braces. Ah, that's good enough. I think it was plus. What was the vector for this line? 1 1 0. 1 1 0. With t being an element of the real numbers. And then the plane is x, y, z equals 1. Okay. Okay. Is it the same type of technique? Let's, so... Why don't we give it a try and see? That would equal -1, 0, and then 2. So I don't remember the answer for this one, so I am just going to try my best and see what happens. Move it to the side a little bit so you guys can see. Okay, so this would be -1 plus 0 plus 2. So we get 3, and then that would be 1. So 1 over 3. And then we just touch it up. Okay. Let's see. I actually have to check this one because I don't think I remember this answer. Y01. So, I learned this from Mavoort yesterday. So, where's my pen? Oh, here it is. So apparently, like, we just have to pick a point from this plane to basically, like, I guess, sort of act as our, like, original, our initial point. So, like, what like point would make this make sense? Because we have a 1 here, so like x would equal to 1, y would equal to 0, and z would equal to 0. So that's why we picked that point. So let's see, 3 square root of 3 over 3. Let's see, back of the book, 4.5. Yep, that's right. Okay. So basically, when it's the plane's distance from like any point or any line, we have to use like a point on the plane itself. That's not the normal vector. Okay. That's a how should I say? I kind of find it funny, like when they teach you this in multivariable calculus. It's like they don't really tell you that much when it comes to that. I mean, maybe in classes they probably show you like the examples, but like I find it funny that like you actually have to like kind of like, I guess, search for the answer, I guess. Like, cause I think like they briefly go over distances that much. I mean, like from like what I've experienced. Because I remember when I was taking multivariable calculus before I dropped out, I was like, huh? Like, how do I find these things? What if t is equal to half on the line? Well, then, like, basically, if it was a half on the line, then basically it would be like the vector 1, 1, 0. It would equal like practically a half, and then 0. So basically you would have to add that by like, you would get the point half 2 at that point. No, it's okay. It's okay. A lot of props don't tell you much except when it's good. When it's a good prop, because the theory is very easy. The derivation is less trivial. Right. I meant negative a half. I mean, practically you would just get a negative half, negative a half, and then 2. Practically. Where would the line be when... I mean, geometrically, it would just be where that point is. Like, negative a half, and then 2. But, like, I guess in physics terms, like, it probably wouldn't exist because there's no such thing as negative times. Are you trying to ask about the distance? Because if you're asking for the distance, then you would have to square, like, practically, like, the negative a halves. Because you're going to have to do the square root, and then you're going to have to do, like, a half to the square and a half to the square, and then, like, 2 to the square. I'm claiming the line touches the plane. Huh. I didn't even think about that, actually. Yeah, I actually didn't think about that, actually. Interesting. Yeah, because then you would get, like, negative a half, and then you add those two together, then you would have, like, you would practically have 1 at that point, like negative 1, and then basically like 2 at z. Yeah, negative 1, and then you get like positive 1, yeah. You said t is a member of the real numbers. I think that's what it said in the problem. Yeah, in the problem it basically said like t is a element of the real numbers. I should have probably moved to the question because you just pointed out, because I forgot I'm using a book. Yeah, t is an element of the real numbers. That's what it said in the question. That's a pretty interesting observation, actually. I didn't realize that. So I learned something new. Another thing, something new. So I'd say the distance is 0. Okay, so where was I? Okay, so basically finished that. Wonder what's the next thing you learn in multivariable. Maybe we should like look into a book now, because these were like the small problems they teach you like for distances. Like, what's the next part of the book? In let me just shrink this about, and I think I'll move our chat here. Oh, whoops! Didn't mean to take the chat away. We'll move the chat like in the center here. I think we can. Let me just click into my tablet here. We'll just move over here. And then we'll just line chat over there. And let's find that multivariable. Let's look at the books that I usually learn from calculus. Calculus for scientists and engineers. This was actually my first calculus book. I don't know why, but I ended up liking this book. I mean, it's very like some of the problems are pretty complicated, but at the same time, I'm like, I actually like it because it's actually geared towards people that are going into STEM. So let's see, vectors in a plane. I think vectors in 3 dimensions, dot products, cross products, line and curves and spaces. Yeah, I think we just learned this one. I mean, we were going over like distances with this one, so I think this would probably be a good way to bring about. He's right, the distance between the line and the plane is 0. Let's take a look here. What you guys put here? Actually, let's put this full screen to see what's typed out. That's pretty cool, though. Seeing, like, this thing. So what is this called? Oh, I probably should, like, put this in my bookmarks. I could probably use this. That's neat, actually. Yeah, in the book they basically say it's -3/3. I don't know, is the book wrong? Because you guys say it's 0, and like, when I look at the book and the way I did the answer, it basically comes out negative. I think you might have been misreading the point for a line. Yeah, the solution. So the solution is square root of 3/3. Unless the solution is wrong in the book. Unfortunately, I can't because I don't have a PDF of the book. Yeah, because like when I look in the back of the book, this is 4.4. Yeah, and it says for F, it basically says the square root of 3/3. And we use the same type of, I guess, this difference that we made between points. We use that same method with the distance between the point and a plane. And we actually got the right answer for that one, which is the square root of 3. I mean, it could be like the solution's wrong. Could be that. But the line goes through the plane. Yeah, I know. Maybe the solution's wrong, or something like that. It could be that. The book's name is No Bullshit Guide to Linear Algebra. Actually, like, let me just do this right here. Assume the line is parallel to the plane. The distance for plane line is the same as the distance plane point. You can choose any point on the line, as any point will have the same distance to the plane. Assume the line is parallel to the plane. Okay. The distance for the plane line is the same as the distance plane point. You can choose any point on the line, as any point will have the same distance to the plane. I have the BDF. What's the page and exercise? The page, I have the first edition, so I don't know if it's the second edition that you're reading, but on my edition, it's page 186, and it's problem E4.5 F. Because, I mean, maybe you guys are right and the problem is just wrong in the book. Could be that, too. mean, we're on break time, so no bullshit guide to linear algebra. Yeah. I actually like the book series, because he also has the book No Bullshit Guide to Math and Physics. I actually like the book because it kind of explains stuff very clearly. Although this was the point where I actually stopped in this book, because I think it's because the distance formulas, I couldn't get them right away. So like I think I stopped reading at this point because I was like kind of confused on like how to get the distance formulas. Oh, I should probably put my model up for you guys because we're in break time, so we can just chat away. Hopefully you guys are having fun with the stream, because usually like exercise number, you mean? It is E4.5. E4.5. Or I guess like they put the E as an exercise, like exercise 4.5. And like I think the letter of the problem is F. It's like F and E are the ones that I was working on and I was kind of struggling with. I mean, I got the right answers, but at the same time, like if it doesn't make any physical sense to you guys, like basically like if the answers are completely wrong for those problems like in the book, then you know, because I trust you guys know more than me when it comes to like the technicalities of how these mathematical processes work. Unless the line is skewed to the plane, they will intersect in 3D. Yeah, because I think I have the first edition. I have the first edition of the book. Because I think like the author basically updated the book because I think he found like some like errors in there. Because like the chapter is geometric aspects of linear algebra, and it should be the first section of that chapter. Because yeah, the first chapter of the first section of geometric aspects of algebra, he starts talking about lines and planes, the geometric interpretations of those, the equations of those, including the distance formulas. Yeah. That's chapter 5. Okay. Yeah, for some reason they call it problems 4. Yeah, for some reason they put 4 in that one. Yeah, because like in my book it's chapter 4. So I guess in your edition it's chapter 5. Yeah, it should be like the first section of the. It should be the first section, and it should be the problems in the first section. You mean parallel? Oh, you're responding to Jeff's message. But thank you guys for actually like looking into the details of it. Actually, Mavoort, are you a graduate student, or are you just an undergrad, or are you already working like in like research or something like that? What version of the book you use? I believe it's the first edition because I bought it when it came out. I believe this is the first edition of the book I have. Because I remember when the book was released, I ordered it. So I think I have the first edition of the book. I have a master's in mathematics, currently unemployed. You asked me that before. Oh yeah, because I wonder, because I kind of forgot. So I just wanted to ask again. But you have a master's in math. That's great. That's cool. I mean, I'm currently unemployed myself too, but you know, like I basically am just like making content for you guys. Like I know I'm not as good in math and stuff, but I try my best to actually try to understand this stuff. Not to get to your guys' level, because I know I can never get up to that. I guess that expectation. I just basically want to understand like the basic stuff. I mean, like, I like looking at equations and basically say, hey, that's a partial derivative, that's a derivative, or, you know, like, I can just pick out, it's like learning a language for me, so it's like, I can look at an equation and just point out, like, what it is. So, I have the 0.9 near the final release. Oh, okay. Yeah, so, I don't know where the exact number falls for my version. Probably like the first version, I guess. Because I have a physical copy of the book. But yeah, I don't know if you were able to find the problem in there. But actually, like, I love the fact that, like, you, well, actually, like, Mavoort, what was your master's on? Like, your master's thesis? You probably mentioned it to me, like, last time you were on, but I just forgot, like, what were you researching on during that time? Because I think, Sascha, he told me he was researching on, algebraic geometry. Actually, I don't remember anyone else's research. If you guys are grad students, or you already have your masters or PhDs, like let me know what your research is in. I know Tyrion was doing some research involving, like, I think you were doing research on like computational physics, correct? If Tyrion is still in the chat. Because I remember you were talking about coding a lot. Finite element simulations for elastic deformations of a rubber pipe. Oh, interesting. So it has a little bit of physics involved with that. That's pretty cool. Actually, I find it funny because, like, with differential equations, like the first part I was able to pick up a little bit. Like, I guess, like, pick up like the methods, but when I read like partial differential equations, like some of the intros, I noticed that every book that I read about partial differential equations, it's like you have to know the system and you have to know the laws of, like, you have to know like the small things that probably don't involve math, but at the same time it's like part of, like, I guess either a physical system or probably part of, like, I guess an economic model or something that you have to put into the model of what you're trying to make, or like the equation that you're trying to form. I downloaded the more recent version of the book. Yes, it has a lot to do with continuum mechanics. Oh, okay. Interesting. Yeah, I think the most recent version of the book, it probably has, like, it's probably going to be a little bit off, like, with page numbers and stuff. So that's something to keep in mind. Now I'm trying to figure out what we can do for the next thing. So, oh yeah, they go over a line. Let's see what we got here. The equation of they tell you to find the equation of a line. I think the next chapter will probably be on distances, right? No, they tell you about derivatives for vector valued functions. Derivative of unit. Yeah. Okay, so that's the same. Okay, so for vector value functions, it's still the same. Okay, so not much differentiation from there. Well, what I mean is, it doesn't look as different as like doing like just a vector with numbers. numbers within them, I should say. Because it's not a scalar. A definite integral is okay. So that looks like it's motion in space. That looks pretty cool. Position, velocity. Yeah, this is when it gets into physics. Let's see. Motion with constant R. R describes the path. Oh, this is circular motion. Straight and circular motion. Yep. So the thing to remember is basically the radius, and the acceleration is going towards the radius. Let's see, a two-dimensional motion in a gravitational field. Let's see, a two-dimensional motion in a gravitational field. So, what is in this, like, what are the problems in this chapter? Let's see, velocity. So you have to differentiate trajectories. So maybe we can do this chapter. This chapter kind of looks fun. Yeah, and plus I like the title, Motion in Space. It's like a good way of learning a little bit of physics with the math. And also, guys, if you like math or physics and you're just lurking or you're new to the channel, be sure to drop me a follow on the channel. It really helps out the channel, as well as it helps inspire me to basically continue on learning more math along the way. You can also follow me on my socials, like basically my YouTube channel. You can basically subscribe to my YouTube channel if you like miss out on some of the VOD in this stream. So yeah, and also join our Discord server if you like to basically talk about math and stuff. Okay, so time's up for break time. So before we continue on, I will just be right back real quick. So let me just. Okay, I'm back, guys. Are you jumping to a different topic now? Well, kinda. Like I did put in the title. It's gonna be linear algebra and multivariable calculus. So I thought I would just jump into one of the multivariable calculus topics. It's kind of related, but at the same time, it's kind of like separate. I think they're related because they deal with vectors. So if you consider it a different topic, we'll consider it a different topic. Okay, so we got velocity, position, so that, yeah, finding out the magnitude, I'm familiar with that. Straight line, circular motion. Let's see, motion in a constant r. Let r describe the path in which r is a constant. So, and the dot product between r and the velocity is 0 because they're supposed to be perpendicular to one another. So let's see. Okay, here we go. Two-dimensional motion in a gravitational field. So I think this one I haven't been familiar with. At least like three-dimensionally. Let's see. Consider an object moving in a plane with the horizontal at the x-axis and the vertical on the y-axis, subject to only the force of gravity, with the initial velocity v at 0, time equal to 0, I should say. And the velocity of the object for time is greater than or equal to 0. Let's see, the velocity is the derivative of those, which is u minus, right? Okay. Let's see, the flight of a baseball is above home plate and the initial velocity in feet per second. If only you went meters per second. I mean, even though I grew up in the US, I really don't like the imperial system. I wish it was meters per second, but that's just a little tidbit. Oh, whoops, I almost forgot to put the study counter on. Because you seemed a bit confused about three-dimensional geometry stuff, I think it would be better to stay on that topic. Like, the thing of it is that for me, like, I kind of get bored easily. So I feel like, for me, I just, like, jump around, and I basically, like, if I run into a wall, I basically just, like, look stuff up, and I basically think about it, like, intuitively. Like, I guess that's, like, me, though. Because, like, for me, like, I just bounce around a lot. Because, like, I think the reason why I stopped with multivariable calculus was because of the distance formulas. Or at least, like, formulating distances. Solutions. The range, flight, so. Two-dimensional motion, assume that the object is a flight of times. I think I've seen these formulas before. Three-dimensional motion. Oh, they have like F equals ma. Interesting. What do we got here? Projectile motion. A small projectile is fired over the horizontal ground and is easterly and an easterly direction with an initial speed of, right? The angle is 30 degrees. A crosswind blows south to north, producing an acceleration of the projectile by 0. Where does the projectile land? And in order to correct for the crosswind and make the projectile land due east of launch site, at what angle from due east must the projectile be fired? Assume the initial speed of the projectile is, and the angle of elevation is alpha 30 degrees, are the same as the parts. Okay. So we have a crosswind that blows from north to south. producing an acceleration. This would be a good practice problem, actually. So the initial speed is... Okay, they have it in meters, that's good. Meters per second, and the angle is 30 above the horizontal. So let's just draw that out. So we'll just, it's probably going to be like that. Alpha is like 30 degrees. And oh no, whoops. So that's the original velocity. So we have a crosswind that blows from south to north. Also, we're gonna have to have it like so I think we gotta have it like this. So the wind is blowing from south to north, and it's X, Y, and Z. I think it's like something like this, I think. We'll just put the angle right here. Okay, where does the projectile land? So if its initial velocity is... So then we're gonna have to calculate it at each okay. A crosswind produces an acceleration of, okay, so we'll just put acceleration of wind. So we'll just leave it at so that would probably be at the y-axis. Now, so then the acceleration of the wind at the x-axis, we'll just assume it's 0 because it's blowing from south to north. But then again, no, you know what? We're gonna do this correctly. Oops, no, not cosine. That should be sine. Sine of 90 degrees. Cosine of 90 degrees. We're gonna make this a little bit more accurate. Okay, where does the projectile land? So we'll just write the question again. Where does projectile land. Okay, so we have the velocities and we have the acceleration. We'll just rewrite them down here so we don't have to keep scrolling back up. And let's just write the angle. And the acceleration of the wind at x. Y at sine of 90 degrees. Okay, so where does the projectile land? Well, when if it's a projectile, then the v remains constant. I mean, the Vx remains constant. So now we have to take into account, so when it's asking where it lands, that's basically asking for its position. So the formula for position in this case would have to be the initial position plus time t half, well actually that should be a minus t. The acceleration due to gravity only affects vertical motion. Right, yeah. Decompose. So now we know that gravity G is equal to negative, and luckily we're doing meters, we don't have to like convert anything. Gy. We'll just put Gy. We don't have to write for x, like the x direction. So in this, well actually I should change these vectors to y. That would make it a lot easier to do. And F for final. There we go. Okay. Now we don't know what time it's gonna end up, so we also have like other equations. So, oops, no. Not y. V final, y direction, is equal to V initial, y direction, plus, well, that's the thing about these equations, let's put negative G to the y times t, and then we have y squared, plus, no, it's minus, minus 2g, difference between y. Okay. Okay. Now. No. Now, the initial position I'm going to assume is 0. Right? So let's see. Let's reread the question. Like a small projectile is fired over the horizontal ground in an easterly direction with the initial speed of the... Let's see. Okay. Let's bring this down a little bit. Bring it to the side a little bit. Okie dokie. Very intriguing problem. Very intriguing. So the final velocity is probably going to be 0 because it's not going to be speeding up anymore when it falls to the ground. And then we'll have the initial velocity at y plus minus gt. Well, technically I don't need the arrows. I probably should take the arrows out. There we go. That makes it easier. Okay. So minus v. We got g, and then to get time, which is vy over g, which we know. So the time, and luckily I have my calculator with me. So we have 300 sine of 30, divide that by 0.36. Oh no. That's another acceleration. That's the wind. Plus, no, like divide that by. So normally it would take like 15 seconds or so under normal circumstances. But then we also have a wind that's blowing in. So I think we have to add that wind parameter in. Meaning that the acceleration will have to be added to gravity a bit. Because it's blowing from south to north. So that means we're gonna have to rewrite this. So instead of just g of t, let's just make it easier and put a plus and minus g plus the acceleration of the wind. Actually, we'll just take the, we'll just put a minus there. Make it easier to see. Oops, no. This should be a minus. There we go. And then those cross out. Okay, so let's see if that gives us divide that and then 9 minus 0 point sine of 90. So the time is 15.9. So it's not too off. I mean, it's not too much of a big difference. You can find the time if I don't say. That yields the total time. Right. So we got the time it takes. Yeah, so then the original is... Okay, so we got like all the numbers we need. So... Ow. Now the fun part. Putting all these numbers together for... Why do I keep putting a vector? So basically we're dealing with the original minus a half do have another acceleration due to the wind, which also makes it there. I think it would be proper to put that in. Otherwise, we'll probably get our numbers off. So let's see if we get this correct. So we have 300 sine of 30 degrees times 15.9 minus a half 9.81 minus the speed of the wind was 0.36. Then we times that by 15.9 squared. So the final distance for at least in the y direction something doesn't feel right. There's something definitely doesn't feel right. Yeah, this is the y direction. I don't think it should be. I'm calculating like it's the x. It just feels iffy. Now I'm feeling a little bit iffy about what I'm doing. Because if we have like the x direction final, and basically it will just like continue on in the same velocity. So we have 3 to the cosine of 30 times 15.9 seconds. That leaves us with 4,009. Now, where does the projectile land? Okay, because now I have to think three-dimensionally now. Because like distance. Okay, maybe it does make sense. I'm just like not. I'm so used to thinking like two-dimensionally instead of three-dimensionally. So it's like because like the z would be 0, and as well. Okay. I think like I'm kind of psyching myself out, but at the same time like I feel as if like let's take a look. What do they give? Maybe I did it completely wrong here. Let's see what they have. Oh, I was way off. Okay, so I have to actually look at what the flaw in my logic was. I guess I was thinking more physically than what the problem was kind of looking for. Let's see what we got. Plus C. Let's see. So the projectile lands at 7,953 meters east and 169 meters north. At least I remember the constant for Earth's gravity. Let's see. Vt is equal to... Oh, okay. Now I see what I did wrong, because I was thinking two-dimensionally instead of three-dimensionally. That's what I was like doing. That's what I was getting off. So, oh, okay. Because like when I did physics problems, I was so used to doing it in 2 dimensions instead of 3, like with an x or y instead of x, y, z. Oops, oopsie. Okay, so substitute 0. Yeah, it's like half this. Yeah, like that's the position formula. Okay. All right. So, did learn a lot from that problem, and like learned a little bit of my blind spots. I did get the physics right. It's just that I did it in the wrong dimensions. If you have time, motivation to go back to 3-dimensional after this, I can share something on. Can discuss on Discord. Sure. Let's see. Let's see here. Let's see here. So that's the last problem you go over. Like, Mavoort, do you wanna like talk? Like, do you wanna have your voice talking in voice chat, or do you like just wanna like continue just typing and you just show me like what you wanna? You just stream what you wanna show me, like how you wanna do it. Because I feel like we can learn a lot from what you have to share. Because I know you've been like suggesting. Do you want to actually be talking with your actual voice in voice chat? Like it's okay. It's okay if you want to like mute it and we basically just stream your screen. I can't go back and forth between chat and drawing. So you're gonna use the actual voice chat. Okay. So you're actually gonna like talk to us. Okay. Alright, So I think I'm just gonna go into my stream VC. Yeah, because sometimes like people don't want to talk in voice chat, so like that's why I asked. Because sometimes they just mute and they just want to like put what they want to show on like the stream. Like they just want to actually just stream their screen and just like show it to me, but just like don't voice. Like they don't use voice. That's why I asked. So yeah, like you can join any voice chat and basically I will just drag you in. Because I have a separate voice chat for like stream and only I can access it. So we'll just open this up. Okay. Yeah, that's why I asked. Yeah, because like, you know, because some people are uncomfortable like talking on stream. So I think we'll just expand our screen because Mavoort is going to give us some knowledge. So I'll just drag our math chat here. But how's it going, Chasu? How are you doing? How you doing? What's the best part of your day so far? Yeah, Mavoort, you can just join any of the voice chats and I'll just drag you in. Okay. Alright. Hey, Mavoort. Welcome to the stream.
Hello? Can you hear me?
Yep, I can hear you. I can hear you just fine.
But yes, echo probably. I need to read.
Yeah. I mean, I can hear you just fine. I don't hear it echo.
Yep. Okay.
If anyone in chat would like to reply.
Headset, because if I don't use the headset, there will be an echo. So
okay.
I use the headset now. Now it should work without echo, right? You can hear me.
Yeah, I can hear you fine.
Okay, then can you click on the link Excalibur, which I have shared in the chat?
Yeah, I already clicked it.
No. Sure?
I think like some of it didn't get included in the link. Because I think
the problem is you need to copy and paste because the automatic generated link stops at the comma.
Gotcha. Okay, so we'll just copy and paste and we'll just paste that in. Press enter. There we go. I think we got it. Okay,
oh, no, it's on top. The rest, maybe just remove it.
Yeah, no problem. We'll just erase this. Oh, whoops. I didn't mean to erase what you put.
Erase everything with Control A or whatever, and then, yeah, or like this. Oh, for you it's dark. How did you get it dark? That's nice.
Yeah, I think you can set it up that way. So you can set it up with like dark screen. Like I think you can click on the side and then
it's
click.
Dark for me too. Oh, it's much better.
Sorry, I'm like kind of erasing some of the lines you drew, but that's.
Yeah, wait.
So let me just like erase this part. Okay, I think I erased everything from there. So.
Yeah.
But thank you for coming on to actually teach us more stuff.
Two lines have been erased, but that's not huge.
Yeah, sorry about that.
I will draw them again.
I'm still new to using this browser program, so.
I'm also new to using this. Usually I use External++, but you can't share external programs. So this browser-based program is better.
Okay. So we got a special treat, guys. Mavoort is gonna teach us some more knowledge.
Okay, I would like to go back to this problem with distance point to line.
Okay.
So we have the line, I have drawn two different pictures because we are going to solve this with two different approaches.
Okay.
So let's start at the first one.
All right.
There's still stuff that needs to be removed. This button. Ah yeah, now it's gone. This weird point. This white point is. So we have a line. No, why can't I draw? I have a pen.
Oh no, we're going over like linear algebra, Jesu.
I can. There's a huge.
We're just doing the distances
It's
between
like
points and lines and planes.
It's too slow. Can't write. It doesn't work.
It's alright, it's alright. Take your time.
Yeah, the problem is I have a it's too slow. Line. You can read this.
I see that you wrote like
Yeah, I want to write something, but it's it's like a ping in a video game. It's very slow until I see what I have written because there is a lot of delay. This is very weird. How do we fix this?
yeah, that's what we're going over, Jesu.
Probably because of the online share. Because when I write without sharing live, then it's immediate and it works. Okay, we have. Oh, hope it works. We have a line. Let's call it L, and it is some vector S. Yes, some vector S. Let's make it green. Plus, usually we choose T times another vector which is the direction of the line. Yeah, this is what you know how to write a line. A vector, which is the point on the line, could be any point, and the direction vector, which I have chosen to call a V.
Right.
We want to calculate the distance between the point P, which is the red here. This is the point where we want to calculate the distance to.
Okay.
So we looking for distance. Oh, distance. Writing is very bad.
It's alright. Just like if it's like lags, just basically just say what you're writing, and then I'll just restate it for chat.
Okay, we want to calculate the distance between P and the
line.
The line. So you can do this technically. It's a bit different notation. I use P for the point you want to compute the distance to, and you had I think P different, but whatever.
Yeah.
Now we have here an angular angle. We have alpha.
Okay.
This is an alpha.
Right.
Can you read alpha?
Yeah, I can read it.
Can maybe write it again? Try again.
Go on. There you go. Yep.
Ooh,
that's
yeah,
better.
Beautiful.
That's very beautiful. Yeah.
Okay. So if we have a point, and let's say we are here at the
tip of the line.
Yeah, at this maybe. Then the point from here to there is not the distance between the line and the point because it's too large.
Right.
We need the minimum. Yeah, we need. This is too large.
Mm-hmm.
This is also too large. We need the minimum.
Okay.
The line where the distance is minimum, right?
Right.
So this is this line, the line which is already drawn before here, the dotted line.
Okay.
Or dashed line, yeah?
Yeah.
So, and how do you know that this is, so this actually is the distance d which we want to compute, right?
Okay, right.
Okay, so obviously, if this is the case and this is the minimum, we have here 90-degree angle.
Okay.
Right?
Right.
Do you see this geometrically? This makes sense.
Yeah, I can see the 90-degree angle from the distance.
So yeah. So if we have 90-degree angle there, just with trigonometry, a sine, cosine, and something like that, how can we compute the distance d?
Compute the distance d. So basically, the leg, which is the hypotenuse, is p minus s. Like that's included in your example, right? The p minus s.
Yeah, it's included.
Okay, so then
P minus s is the hypotenuse.
Yeah, and I'm guessing the vector v right there with the line. V is only covering like that to the head, right? It's not including like the line bit that's like touching the 90-degree part, right?
Yeah, but ignore the v at the moment. Just
well, simply like let's just say
you are given the sides.
Yeah.
Maybe call them A, B, and C. You have the sides of the triangle, the hypotenuse, the Ankathete and Gegenkathete. I don't know the English word. You have both sides and the hypotenuse, and you have this angle alpha. How can you compute D?
Yeah, so like if we're using just regular trigonometry, it would probably be like, I'm just gonna call the bottom where the alpha is touching that leg. I'm just gonna call it V anyway, since you just have a V there. But I'm gonna interpret that as V, and like the other leg is gonna be D. So to get D, we would have to basically it's like sine and cosine. So this would be, so we have the hypotenuse. Wait, I think I can write as well, right?
Yeah, probably.
Okay, so let's just say we have V. So
you have to write very carefully because of the leg, because of the ping.
Right. Okay, so we have two legs, which is, so we have alpha. Oops. We have alpha. So cosine, sine, and tangent of alpha. So if this is touching, so we need tangent. So we only have, so it would be, that's cosine and sine. So D, and then V would be equal to tangent of.
V is not the complete. It's shorter. I have drawn it shorter, and there's a reason that it's shorter, because V is not the entire length of the
so let's just
side.
So let's just call it V plus A. Let's just call it V plus A.
Yeah.
Call it that way. Yeah. So then
I think it would be better to scale it, like S times V or something like that.
Yeah, that's probably better.
Because
we'll just put it like no, actually I'll do a little better. Let's just make it like that.
Okay, great.
Yeah, and then basically at that point we can just multiply this to equal D.
Okay, good. Problem is we don't know lambda, we don't know the scaling factor.
Right.
But maybe sine or cosine will be helpful. Tangent is not helpful, obviously, but sine or cosine might be helpful.
Okay. So let's see, for cosine, we would have to do basically the I over the hypotenuse, so it would be lambda v over ps minus s, and then sine would have to be d over the hypotenuse, so then it would just be,
Yep.
yeah, you're right. Yeah, this is easier, I think.
Parentheses, don't forget parentheses.
Yeah,
P minus S. Okay,
There we go.
so this is what we have, this is what we want. P d equals, I write it to the left side. If you're scrolling, scroll to the left. I'm writing the exact same what you have written. D equals P minus S. These are vectors, so we need to take the absolute value because this is the length, times sine of alpha. Okay? Okay. So this is already important. So geometrically, we derive this just with trigonometry. Now, do you know these formulas? If there are two formulas with that contain alpha. For example, if you have a times b, the scalar product, the vector, and then you compute the length. This is the length of A times the length of B
As the cosine, like
times cosine
of the angle between them.
Ooh. No, this is writing like this is inconvenient. Yeah, but you know this formula, right?
Yes, I know that one. And
Okay.
the cross product
Do you know
is
a
basically
similar-
this side.
Do you know a similar formula for the sine?
That's the cross product of the vectors. So basically, it would be the magnitude of a vector A and the magnitude of vector B times the sine of alpha times like a normal vector.
100% correct. The magnitude of A times B, the cross product, is the magnitude of A times the length of B.
Hello, Aminux. Thank you for the follow. I appreciate it.
Times sine of alpha. Okay?
Okay.
So, if we want to compute P minus S times sine alpha, then we need to divide by the other, by V.
Okay.
So, I scroll up, scroll down. Oh, wrong button. So if we have B times sine alpha, because this is what we want. We don't want, we have A times B times sine of alpha,
Right.
but we only want B times sine alpha. So we need to
So why do we need only B?
because we have P minus S times sine alpha here. This is B.
Oh, that's all B. Okay.
Do you get it?
Yes.
So we want B minus S times sine alpha, but if we do B times P minus S times V, cross product V, we
Yeah.
get P minus S times V times sine alpha.
Okay.
Yeah? So this is a cross product. Divided by the length of vector B. A, of course, not B. A. Okay?
Okay.
Yeah. So
Oh, okay.
Now that we know that,
Mm-hmm.
I will move it a bit down because this is just red. We can apply this here. This means that D is, well, how would we apply this here?
Okay, so basically, like if P and S, and then we have, because before we had P and S times sine would equal D. So we're still trying to find D, correct?
Yeah, we still trying to find D.
Okay, okay. Alright, so then we already have B, which is PS. Yep, P minus S. And then we have, I guess, our special vector, which is like lambda V.
Yeah, forget lambda V. How do we get the sign? You said the sign is important because we get the sign with a cross product. A times B is a cross product. Also norm of the cross product A times B is norm of A times norm of B times sine of alpha. Here. So what is A, what is B if we have sine alpha like written, if alpha is the angle between these two vectors?
Okay, so basically, because like now I'm thinking about the projection, like between like V and P minus S. So like so A and B would probably be like V and P minus S. So I think it would be the cross product of V cross P minus S, and that would be over that would probably be over, I would have to say V, like the magnitude
correct.
of V, right?
What we have here is the cross product of P minus S. We need to use parentheses, of course. Cross product with V. And now the magnitude, the length, divided by the length of V. Okay?
Right.
Because P minus S cross product V is equal to length of P minus S times length of V times sine alpha.
Okay.
But we don't want to have P minus S times length of V times sine alpha. We only need P minus S times sine alpha. So the times V is too much. We don't need it. So how do we get rid of it? We divide by length
the magnitude.
Of V.
Okay.
Yeah.
Yeah.
So this was what we have here is the exact same thing as what we have here at the bottom. Yeah.
Yeah.
So if you have sine, you use the cross product, and if you have cosine, you use the dot product.
Okay.
And now we are finished because this is the formula for the distance. Ooh, I just want a border.
It's all right. Like, take your time. There we go.
Like this. This is the formula which we have derived now, just with using geometry.
Okay.
But you see, this formula makes sense. P minus S times a cross product with V is P minus S.
Yeah.
The length times length of V times sine alpha. But the length of V is too much, so we divide by length of V, and we get P minus S cross product with V divided by length of V. And this is the same as length of p minus s times sine alpha, and because of trigonometry, this is the same as the distance d.
Oh, okay. So this is the minimum distance, right? Like the shortest distance between them.
This distance is always the minimum. So if we have a convex, if it's not a line but something different like a donut or whatever, it would be the minimum always.
Oh, okay.
So this is one formula. But this is not the formula you have used. This is a simpler formula. You have used a different formula, which is a bit more complicated.
Okay.
Right?
All right.
The advantage of this formula is that you get the distance directly, but maybe you don't want the distance. Maybe you won't actually compute the point, where it's actually minimal. So this point, and you are given the question, where is this point? L. Let's call it L. Yeah.
Yeah.
So how do we do this? Scroll down. This is the second approach. Yeah.
Yeah.
Okay. Here you see the point L. This is what we want to compute. If we know the point L, then we can compute the distance easily by getting distance between 2 points. Distance from the line to the point P. Here's just P again. Why is it red? Here's P, like before, exactly the same problem. And if we have this, then this is the dotted line here is of course the distance. Yeah.
Yeah.
So, but what if we don't? So the distance then is just d equals L minus P, and then the length of this, right?
Oh, right.
Okay. So the difficulty now is how do we compute L?
Okay.
Yeah. Okay. So now, if we think about this, you could see it as an optimization problem. If you see, if you define the function again, f of t from before is equal to s. Well, s was green. Now let's just copy it from the top. It's this. I just want the copy. Paste. Here it is.
Okay.
So line was s plus t times v. It's the same line as before. And we call this now as f of t instead of L, because it's a function of t is any number, so it's technically a function, right? It's a function. That's also how it was drawn in GeoGebra. It's a function. So let's say you have a given point somewhere. Let's say it's here. This is supposed to be on the line. So this is yet f of t. F of t here. So it's think this is on the line, right?
Okay.
It could be any point on the line.
Okay.
So now this distance.
Right.
It's not the best distance, but we will get to that.
Okay.
So how would we get the distance that I have drawn here, the white line? F of t and p.
F of t and p.
Yeah.
Are we given the coordinates of that particular point?
You are given t. T is, for example, 3. And the point P is, of course, also given. It's the same point from the exercise.
Okay. So is it from the line to just the point, right?
So this is just a point, and the other thing is also just a point. F of t, I mean, everything on the line is f of t, of course, but I mean, this is very specific f of t. Maybe I was not clear how to...
So to calculate the distance, like if we're just doing that specific point, basically it would be like the distance formula. Like we basically...
f of t minus
p, yeah, the typical distance formula.
And now of course the distance.
Yeah.
So this is just the distance, but we want this to be minimal. Of course, this should be minimal.
Okay.
So let's say it's supposed to be min.
Right.
Okay.
Yeah.
So how do we get the minimum of a function?
I think we would divide it by the actual length of.
No.
It would be.
How do we get the minimum of any function? Let's say the left side is a function, and we draw it, and it's like something like this. Like f of x is, I don't know what. X squared plus.
Usually you would take the derivative of it. And
Derivative, exactly.
And then see where it hits 0.
A function is minimum where f prime of x equals 0. Yeah?
Yeah.
So this just keep in mind.
Yeah.
So what we need to do is we can compute the derivative.
Okay.
So we compute the derivative. With respect to t on both sides.
Okay.
Yeah. So now we have chain rule outer the f of t. I will we need d by dt s plus t times v, because f of t was s plus t times v. Minus p now of this.
Okay.
This is equal to 0. Yeah?
Yeah.
And when we get this 0, we will do some calculations to compute t, a very specific t. And when we have this very specific t, we know that s plus t times v is the point L which we are looking for. Okay?
Okay.
So let's calculate this derivative. How do we ask? This should be is chain rule outer outer derivative times inner derivative. So we have a gradient s plus t times v minus p times the inner derivative, outer derivative times inner derivative, but outer I haven't computed yet. Just the outer derivative would be this, and the inner derivative would be just v, of course. S plus t times v minus p, f something which has nothing to do with t, so the s and p is just constant, and the v would just be the inner derivative. So now we have to know that this is s plus t times v minus p divided by the length of s plus t v minus p. And now this times v. It's a rule like gradient of norm of x is equal to x divided by norm of x.
Oh, okay. Yeah, I never knew that one.
You can, like, yeah. So this is 0. Okay?
Mm-hmm.
So how do we compute t? Can we maybe get some other, can we make it easier, the left-hand side? Some, Termumformung.
So basically, we just want t, right?
We want t, yes.
I mean, like, that dot is supposed to be like, is the dot supposed to be like a dot product, or is it just multiplication?
It's...
Because it's a vector, so it's like a dot product, right?
It's a dot product, yes.
Okay. So, I mean, then basically it would be like s over the s plus t x, plus t times v minus p. I mean...
Well, we could multiply both sides with
the length
denominator.
Yeah,
right?
that's what I was thinking about.
Yeah, so we have s plus t times v minus p. Scalar product, dot product times v equals 0. Okay. So now how do we continue?
I think we can just commence with the dot product of v to s plus t v minus p, and then and I think we basically bring all the terms that don't have t to the other side.
Yeah, we have on one side all the terms that have a t, and on the other side we have all the terms that don't have a t, so that we can solve for t.
Hey Sascha, how's it going? What's the best part of your day so far? So then we would have like did you ask a question like during that? Sorry, I was talking to chat.
You mean me?
Yeah, did you ask?
We are still solving for t. Maybe you can simplify this. Your idea to bring the term with has t on one side and the term that doesn't have t on the other side is already a great idea.
Mm-hmm. So you want me to start writing in your...
Yeah, why not? If not, I can just...
Okay, I'll just drag this down here. Just right. Okay, so... let's just make this v... Oops, no. Don't want that vector symbol there. So... it's vx, vy, vz...
Okay, maybe we'll just delete that. I mean,
I'm just trying to visualize it in my head. That's why, like.
So I'm just wondering why are you using vx, y, y, and z coordinates. What we are doing right now works in n coordinates. It's not.
It's not three. It's not three-dimensional. Yeah. Okay, that's what you mean. Because I know, like, what is it?
So like, you said it already. We need.
This section is like one whole vector, right?
Yeah.
Right. Okay. So then it's just the dot product, and then basically all the components will just basically like be together. So I think the only component that will have t in it is basically vt, which will then be
okay.
like
S. Let me write S minus p times vector v is equal to, do you know?
let's see, p minus s, and then basically it would be like minus t v squared.
Yep, minus t times vector v squared. Now we are very close. We still want to compute t, so how do we get t?
Divide the magnitude of v squared.
So t equals say or write yourself. You said it right what we have to do. This was the correct approach.
Yeah, so wait, is the negative, like since t is negative, right? Do we have to multiply by -1 to get rid of it?
Yep.
So then just negative there.
Yeah. Just one remark. Instead of saying minus s minus p, I think it would be easier to say p minus s.
P minus s? Yeah.
Yeah.
To make it look nicer, right? So
yeah, because minus parenthesis s minus p is the same as p minus s.
Got it. All right, here we go.
Yeah. Do not forget the dot. The dot is important because we have actually a dot product here. Mm-hmm. Yeah.
Right.
So this is t. Now that we have t, how do we get L? We still wanted to find the point L, where it's actually minimal.
So that is equal to t, right? So then we basically have to have f of t equal to L.
You know f of t we have given vector s and we have given vector v, which v was the direction, s was any point on the line.
Yeah.
And we don't know f of t is s plus t times v. Now that we have computed t, we just have to plug it in.
Yeah.
Right?
Right.
So
then that's also with v.
Yep, exactly. Let's make parentheses to make it exactly. This is L. Correct.
Oh, okay. So yeah. So
this is a bit confusing. The first dot is important because it's a dot product. And the second part, it's important that there is no dot because this is not a dot product. What we have in the parentheses is just a number.
All right.
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 Vector times vector is a number, and number times vector is not a dot product. It's just normal scaling.
Mm-hmm.
Okay. So this is L.
Okay. So basically,
let's move it down and make a red box. Oh, I fucked up again.
That's okay.
I will move it down because this is important, and I will make a red box around it. Because now we have it. Now we have L.
Okay.
So now we said that the distance between the plane and the now point. we just need this minus p. then we have the distance.
So basically minus like L minus P, right?
Yes.
Alright, so then just L minus P, and then that whole thing would be S plus... I'll probably move to the side a little bit so that chat can see it. So do that. That dot product V. And then that's all minus P. Oh wait, P is a point, right? It's not a vector, right?
P is a vector. P is
it's
a
a vector.
point where we want to compute the distance to.
Okay.
So this looks good to me. Yeah.
Alright, what's next? Or that's it.
That's it. So we said distance is where is it red? Distance is L minus P. This is our distance, so we need to it's a bit, I would write it like
Go on.
this.
Yeah.
S plus P minus S times vector V divided by V squared applied to vector V without dot product, because this is not a dot product again, minus P. And now just we need... So this is the same formula. I have just written it like this because now I don't need two levels of parentheses, which makes it a bit more readable.
Oh, okay.
You see?
Yeah.
And this formula is now the distance. This is the formula which you have used for solving the exercise.
Okay.
So if you have just got it somewhere from the book or from Wikipedia, I don't know, and not know where the formula is coming from, now we have derived it. Yeah.
Oh, okay.
Just last thing that I would like to say is, we derived it with differentiation, with the derivative. Because, well, why is it derivative? Because we said we need the minimum distance, which is, and minimum, a function is minimum if it is 0.
Right.
Right. But there's also a geometric interpretation, which is, if you look at the drawing of the plane again, if you look at the plane and the drawing, so what do we know about this plane? What's the normal vector of this plane?
The normal vector of the plane?
Yeah.
Usually it is perpendicular to the plane.
Exactly. Yeah, that's what it's meant. But which vector is it?
Which vector is it?
Yeah.
Well, if it's perpendicular to the plane, it usually like comes pointing out of the plane.
Yeah, but I mean PSV, which one?
Oh, are you asking about these vectors here?
Yeah, exactly.
And we're talking about this plane that you drew right here, right? Like the one with the L in
this
it?
Is supposed to be a plane which is which
I think would be P because it's on the plane. Like by the
P is
point.
on the plane, that is correct, but P is not the normal vector. I was asking for the normal vector.
Oh, the normal vector. I don't know if this arrow that's pointing out in the center where L is. I don't know if that's pointing out of the plane or is that with the line?
That's pointing out of the plane. I can't draw 3D things.
Yeah, it's 3D. It's fine. But
so,
yeah, go on.
So this is the normal vector n, and what I was trying to draw here is that the normal vector of this plane is in the same direction as the direction vector of our line. So n is the same as v. Okay? N is the same as v because that's how it is. We need to construct a plane which with two conditions. One, that the normal direction of the plane is the same direction as the how do I... This should be a right angle to the
plane.
Yeah. So the normal vector is perpendicular to the plane.
Right.
Yeah.
Yeah.
So and we have another point in the plane which is P. So we can use the Hesse normal form. Let's say this plane is the same as n times vector x minus p. That's equals 0.
So what is vector x in this case?
It's any vector in the plane.
Okay. So it's the dot product of like any vector in the plane minus the actual point.
Okay. Maybe I need to draw another thing. I will draw it here at the bottom, or to the right. Okay. It's a bit difficult what I want to draw. Let's give some time.
Like while you're at that, I'll probably talk to chat for a second. Thank you for the follow, Road Frank. Let's see, Sasha, what did you say? I talked with my advisor. I had a very nice. What'd you talk with your advisor about? Like more on your research, I'm guessing. But thank you for showing us all this, Mavoort.
No problem.
It's a lot of knowledge. Like I'm like, okay, now I see like where the formula is derived.
We have plane again. And
right here.
We have wrong direction. Hello, you guys studying math here, but I'm far behind you.
No problem, Rogue Frank. Hopefully I'm pronouncing your name right as well. But yeah, like, you know, like I'm just basically studying math as a hobby, so, you know, I'm not, like, I'm probably behind all of you.
Is the point. The red one is another point. Let's call it X.
Okay.
I write X here. Hello. Where can I write?
The red one is X, right? The red arrow.
Yeah.
Right.
I need to.
You want me to write it for you?
Yeah, write X.
Vector X, right?
Yeah, maybe do it red because it's pretty. But yeah, okay, it doesn't matter. And the other one, the other arrow that I have drawn is, let's call it A. A is good. Yeah. And now we need a normal vector of the plane, which would be kind of this direction, right?
Mm-hmm.
If it must be orthogonal to the plane.
Mm-hmm.
Make it a bit thicker. Yeah, perfect. So this is now it works. This is n.
Okay, you got it.
Yep.
There we go.
And let's make this green. We want to call this A.
There we go.
I think it's better if we do it like this.
Color code it, yeah.
And it's a bit okay. And this was X. We have it red.
Okay.
Now larger. Okay,
There we go.
great.
All right.
So X is another point of the plane, and
Mhm.
A is the point of the plane, and N is perpendicular to the plane.
Okay.
So N is the normal vector. That's why I called it N, normal vector.
Mhm.
So it's perpendicular to the plane. So if I get this vector,
Mm-hmm.
what is this vector?
That vector.
Yeah.
Is it perfectly perpendicular to n?
Yeah, because if X is in the plane and A is in the plane, then X minus A is in the plane.
So it's the distance between vector the point A and the point X on the plane.
It's not the distance, it's a vector. Distance it's just a number, but it would be
Mm-hmm.
So this is the perpendicular because this is a normal
90
vector,
degrees. Yeah.
and this is X minus A, right?
Mm-hmm.
X minus A, the vector.
Okay.
So what we have here is a condition X minus A if we scalar multiply it with a dot product times n, and this is 0.
Okay, that's like similar to what you wrote before.
Yeah, but the question is why? Because X minus A times this is perpendicular. This is the same word we had before.
Yeah.
X minus A times n is X minus A
Mm-hmm.
Times length of n times cosine of alpha. Okay?
Okay.
But alpha is 90 degrees, so this
Right.
is
0.
0. And n is always 1 because n is normal vector. So it's
Right.
we assume that n has length 1.
Mm-hmm.
So this explains that if we have a point x that is in the plane,
Mm-hmm.
then x minus a times n equals 0.
Oh, okay. Okay.
What?
Yes.
Lagrange vibration on hypercolor manifolds? I have never heard of that.
Yeah, because Sasha, aka the Kyler Combe, he is doing a thesis on I think it's like algebraic geometry, right, Sasha? Yeah, that's why it sounds like like very intense stuff.
Sounds complicated.
Yeah, it's
Whatever. I just wanted to draw this image so that you understand where this formula here is coming from.
Mm-hmm.
x minus a times n equals 0. Why is this the case? Because x minus a is this vector here in white, which we have drawn in white, x minus a, and it is a 90-degree angle between this and the vector n, because x minus a is inside the plane, it is living in the plane, and n is perpendicular to the plane, and because it is perpendicular, we know that this is 0.
Oh, okay.
Okay? Yeah.
Anything else you would like to share with us concerning the topic, or that's about it?
Yeah, I'm...
Because you've taught us a lot, so like I'm just like wondering like if there's...
So yeah, two things. First thing, we can use this to what if x is not in the plane? So like this. This is we will discuss later maybe, but not now. What I wanted to say is here the image, you see my mouse cursor.
I'll
right?
follow your mouse. Okay. Don't worry.
Nx minus p is equal 0 is the same principle. So now we have n, but instead of a I have p, because a is just a point which is inside the plane, right? And n is a normal vector. So p is this point, because it doesn't matter, I just need one point in the plane, but this point p, where we want to compute the distance between we still want to compute the distance between the line and the point, right? And this point p is inside the plane, so I can use it for a.
Okay.
So this is what we have, and n was v. So I have here, if we plug this in, I will do I am getting crazy. A. So n times x minus a from this formula basically, right?
Right.
So n we set is v, and a is p.
Okay.
Because we need just any point, so we have v times x minus p equals to 0 for any point that is in the plane.
Okay.
Hello, Femvox Fun.
Hey,
we are doing
Femvox.
3D geometry. Okay, this is the plane. And plane. Ooh. Oh god. P L A N E. So it's line. I can copy it again. Where was it? L is here.
I think L was like at the bottom.
Oh, I have it here.
Like you just want to put them together, right?
Yeah. So we have a line and we have a plane. So what we are trying to compute is the intersection between the line and the plane, because L is the intersection. L is the intersection between the line and the plane.
There's a T between
Yep,
between,
I corrected.
Yeah, there you go.
So how do we get this intersection? Just plug it in for x.
Oh, is that why you replaced the normal vector n with x? I mean with v.
Well, because we need specific numbers. N is the normal vector is the same direction as the v. Yes. So how do we plug this in? Can you continue? We want to compute the intersection between a line and a plane.
Intersections between the line and the plane. So we have V here. So do I have to solve for V for the line in the line of the equation of the line?
You have to think like this is vector x, right?
Right.
So we said L is s plus t times v is any vector. So this could be x, or this could be x, whatever, right? So s plus t times v is x, and we plug x here. I remove this to get a bit more space. Just in here. Correct. So now if we solve for t, this means that we solve the t where we get the intersection between the line and the plane. So yeah, you see we get, this is the same approach. So the difference is, this is just a geometric interpretation where we say we are computing the intersection between a line and the plane. And before we had a more calculus or analytic approach where we said we calculate the point where it's minimal, where the distance is minimal, so we calculate the derivative. But it's the same. What we are doing with the derivative is it's minimal where it's the intersection between the line and the plane. It's the same.
Ah, okay.
That's what I wanted to say.
Okay.
Yeah.
I see. So
now we have derived basically two formulas for the line, distance line and the plane. Well, this was nice. We have this with the cross product at the top. And we have these, if we compute this with the L, if you ever get the exercise, compute the intersection L, you have this. So this was everything I have to say about distance between line and the point.
So basically the two formulas that you boxed in red, basically the one with L is basically from the line to the plane, right? The line to the plane or line to the point?
If they are both from the line to the point.
Line to the
from
point,
point
right?
P to but L is the intersection. So if we have L, then the distance is this L minus P, and then the length, of course.
Okay. And for this, and the other one you put in red, that's the distance between basically like a point to a line.
Where are you?
On the top underneath the line, under the equation of the line.
Yeah. This is the distance between line and point.
Point, right. Okay.
And this at the bottom, which is below the red, is also the distance between line and the point. These are different formulas for the same thing.
Okay.
This, I might... this is the distance between a line and point. Okay?
Oh, here we go.
Yeah. So maybe...
Between line and a point P. Okay.
The only thing that we might fix is what do we do if we want to compute the distance between a plane and a point. So we said if x, I have rescaled this x, if x is inside the plane, like this, we said x minus I, a times n equals 0, right?
Right.
So now assume x is a point somewhere in space, like this maybe. And we want to compute the distance.
Okay. So...
Yeah. Yeah, maybe like this. So, I'm not sure how I should draw this. So now this is of course x minus a. This is good. I draw it like this. And this is x minus a. Before is the white line. X minus
a.
A. Everything is a vector, so this should go this. Okay?
Okay.
So now we assume we have a bit of a projection like this. And like this. Now the distance would be where we have here a right angle. Right? And the distance is this. Correct?
Okay.
Do you see geometrically that this is the distance?
Yes.
Yes. Okay. This is the distance. Do you have an idea how we can compute the distance now? Just using this image and geometry.
So
the same as before, something related to sine and cosine maybe.
Yeah.
Where do we have angle? You need to think for yourself.
Yeah, so we have a 90-degree angle here, and so is the hypotenuse, is this basically cutting in half the 90 degrees that we made with the n?
If you mean with cutting in half that it's in 45 degree, then no.
Oh, okay.
Let's
so basically,
say
so the n is it's still 90 degrees with x minus a. That's what I'm asking.
No, the n is orthogonal to any point, any line that is in the plane, and this line here, the dotted line, is in the plane. So this is orthogonal.
Okay.
Maybe you need the 3D plot to see it better.
Because I would think like we would use the angle like right here. I guess we'll call it alpha, this angle. And then basically we would have to use trigonometry to figure that out. So it's like sine of alpha.
Okay, maybe it's not sine. Wait. maybe I will rephrase my question. What is the this vector, if you think, what is the direction of this vector? Not the length. What is the direction?
The direction of that vector?
Yeah.
Well, it's pointing what looks like it's like the east-north direction.
Yeah, but it's perpendicular to the plane.
Yeah. Actually, it kind of looks like it's, oh yeah, it could be like perpendicular to the plane, yeah. It's like the same direction as, N.
Exactly. This is the same direction as N. Make it blue. I'll make it blue. I can't. Why can't I make it blue? I need to use this. Oh no, it's blue. Perfect. Make it thick and dotted. This is in the same direction as N.
Mm-hmm. Let's see. So this is 90. We have alpha. We have this, and we have this angle.
This could be too large again. So it would be, I'm drawing here an N. Vector N.
Mm-hmm.
Okay?
Mm-hmm.
Just, it might be differently scaled, but this is the length, the direction at least. So instead of the alpha which you have drawn there,
yeah,
we will use a different alpha. We will use and remove it.
You want me to erase it?
Yeah, this would be nice. Let's make it. We will use this alpha.
Okay, so
I will draw a bit. It's not better, but whatever.
well, we can see it.
This-
yeah,
This is alpha, right?
right.
This is alpha.
Mm-hmm.
X minus a is the hypotenuse because this is opposite of the right angle.
Mm-hmm.
Yeah.
So like, I mean, it would look like cosine of alpha. So then cosine of alpha, and then that would be
Okay.
Let me just drag this over so that
So,
you guys can see it.
So yes, n is the okay. N is just the direction.
Right.
The distance is what we want to compute. So it's actually the distance. Let's call it d.
Mm-hmm.
Maybe I'm just not drawing good enough. Let's make the n away. This is the distance, and n was just the direction. So you can't divide a vector by a vector. At the top is d. Exactly. It's not n because n is just the direction. We don't know that this is the direction, but the length we don't know. Okay. So the length of n is 1, because we assume it is 1. The distance is x minus a times cosine alpha. X minus a times cosine alpha. This is correct.
Okay.
This is the distance. You see this? X minus a times cosine alpha is the distance. So
Right.
this is already what we want.
Okay.
So the problem is here again. How do we get cosine alpha? Same principle, except that we, like before, just now we need to replace cosine and not sine.
Okay.
So what do we do?
So, like, could you restate the question? Did you?
Well, if I give you an x specific point and a point A, and you want to compute the distance, and you have and how do we compute this? You don't know alpha. How do we compute? How can you replace the cosine alpha?
Just to basically get like x minus a, the distance between that.
I mean, we know it's from before the A times B equal to A hello times B
Hello, ultimate.
times cosine of alpha.
Ultimate. Thank you for the follow.
Yes, what is the question?
Yeah, what is the question, Goofy the Ultimate? And thank you, like I said, thank you for the follow.
Also, maybe one we cannot. Okay, then maybe later. So this means if we divide by B, we have A times B divided by B equal to A times cosine of alpha. You get it? What I mean?
So the bottom one, like so it's like the dot product of the length of the dot product of A and B. Is that supposed to be a B underneath?
Yeah, this is a B.
Okay, so it's then like so basically it's on the other side. It's the length of A cosine alpha, right?
Yeah, this is length of 8 cosine alpha. I haven't drawn perfectly.
It's okay.
I can draw again.
Okay, so I guess you're basically asking me like.
I'm just saying that the idea is the exact same as before, where we had it with sine. Where we had it with sine, we replaced it with the cross product. Now we have the cosine in our formula. Now we need to replace it with a dot product. So how can we do this here?
Okay, so I think we would have to divide. No. Let's see, the cross product was. So there's two different. It's not a dot product. It's just the difference.
It is dot product. You have just to think what is A, what is the one vector, what is the other? One is obviously x minus A.
Yeah.
What is the other?
The other vector.
Uh,
That's n, isn't it?
It's n. we have this one. The alpha is the orange angular or angle. The orange thing here. And x minus a is the white line here, is one vector, and d times vector n, the distance times vector n, is the blue. So what we know is, if we do the same here, we have x minus a times vector n equal to length of vector n times, just remove this stuff, whoop-de-doo. N times x minus a times cosine of alpha. You see, this is the same?
Yeah.
A times b is a times b times cosine alpha, and x minus a times n is n times x minus b times cosine alpha.
Okay, so the question originally is supposed to be, how do we get d? And if it's the way you described, so I think on the bottom, would it be
yeah, close. At the left we have a scalar product, so you multiply just the length. You need x minus a times vector n divided by,
because n is hypothetically like 1, right? So
it's this vector which is perpendicular to the plane, and now divided by the length of vector n.
Oh, okay.
Okay?
Yeah.
And this is now
d.
This is x minus a times cosine alpha, and we have said that x minus a times cosine alpha is our distance.
Okay.
Yeah?
Yep. Okay.
So this is interesting because now we have a distance formula for a plane and point.
Okay. I think that will do it for today's stream, guys.
Yeah, I think this will be enough for today.
Yeah, thank you, Mavoort, for teaching us all that. That was very, very informative. Will this link remain like on forever? I could probably like...
I don't know, but it's definitely possible to download this. Where you click on the burger menu in the left and click on Save As, and then you can download it. I want to make a red box around it, then we are finished.
Nah.
Oh, there is already a red box. So we have, you see, I said x minus a times n equals 0 is here the red box. But if I divide it by n, yeah, this is our distance formula. So I could also say that this is the distance formula and just assume that n is length n. So I write assume length of n equals to 1, then this is a distance formula. Maybe better like this.
Assume length of n is equal to 1. That's what you wrote here, right? Yeah, that looks better.
And this.
Okay. All right. Thank you for like all that information and all that teaching, Mavoort. Much appreciated.
Yeah, no problem. I just wanted to get a geometric interpretation of how the distance between line and point, line and point works, and distance between plane and the point. Because if you just get the formula but don't know where they are coming from, you need to. It's not good. You can just plug in numbers. You need to understand the formula, and I think this is better like that.
Thank you very much for the very informative lesson.
Yeah, no problem.
All right.
I hope the link stays.
Yep.
You can download it if it doesn't stay, the link. I downloaded it.
Yeah, I'll probably like...
export. Did you download it?
Yeah, I'm just making, I'm just downloading it a little bit, just in case. All right. Okay, guys, thank you for joining me on today's stream. I know today's stream went off a little bit longer than expected. Thank you, Mavoort, for all the information and all the visuals. I'm pretty sure it was really hard to draw those things.
Yeah. It's because of the lag, because of the ping when it's sharing. If I could just share my screen and do it locally,
yeah,
instead of this program, then it would be better.
Right. But like, you made the effort, and that's most appreciated, especially for my channel, and especially for my education into math and physics. So again, much appreciated, man. I will like log off the VC, so to get back with chat.
Okay.
All right. Thank you very much.
Bye. Nice evening.
Okay, guys. Let me just put my model up so we can say. So I hope you guys got a lot out of that. So for all those that follow, thank you very much for following. Like a lot of you guys, we basically had like 3 people follow, so thank you, Aminux, or Aminux, hopefully I pronounced that right. Thank you, the Ro Frank. Sorry I didn't get to talk to you guys as much, but guys, have a nice evening. Thank you, the Rogue Frank, and the old Goofy the Ultimate. Thank you for the follows. So if you guys are joining for the first time, yeah, like, and if you like math or physics, drop a follow. And also, if you guys have just joined already and just dropped a follow, and you wanted to see what we did at the beginning of the VOD, I will upload this VOD on YouTube. So be sure to subscribe to my YouTube channel, so that way you guys can probably keep, like, you know, updated on the vlogs that I'm doing. Or if you just need a little background noise for like studying or like doing anything that you're passionate about in front of the computer, you can also put my streams up if you like, or my YouTube videos. And if you're watching this on YouTube, you know, drop a subscribe, and probably you can tune into our next Twitch stream. All of the descriptions are down below, and if you guys want to continue like chatting amongst yourselves about math, including doing math and physics with me, you're more than happy to join our Discord server as well. Okay, so let's see if there's anyone doing any math content right now. Dawn Does Math is streaming, but they're playing a video game. But we're gonna give them a raid anyway, because Dawn Does Math does math content as well. So I might as well just like introduce you, bring you guys over to his channel. He's playing a DZ Daisy. So let's just like give him a awesome hello. So this is the raid message, so you're more than happy to copy and paste that if you like. Let me just copy this. Okay, and now we'll just do the raid into Don Does Math. Alright, the raid is set up. Well, once again, guys, I thank you guys for joining me today. And always remember, everyone is precious. You guys are just as precious as everyone else. And I will see you guys next week. So take care, guys. Bye-bye.